In the periodic table, group 1, 2 and group 17 are the most reactive group.
Atoms tend to be reactive when their valence shell or outermost shell is incomplete. Each halogen element has 7 valence electrons in its outer shell, so they require only one valence electron to form a closed shell, which makes them very reactive.
Group 1 alkali metals and group 2 alkaline earth metals are the most reactive metals in the periodic table. The group 1 need to lose only one electron, and the group 2 also need to lose 2 valence electrons to form a closed shell. They readily give up their valence electrons to achieve a full outer energy shell, which makes them very reactive. In fact, group 1 alkali metals are so reactive, they are usually stored in the mineral oil to prevent reaction from air. The halogens include the 5 elements chlorine, fluorine, bromine, iodine, and astatine. They make up column 17 of the periodic table. None of the halogens exist free in nature because they are very reactive.
Like halogen, group 1 and group 2 elements do not exist free in nature.
They are all found combined with other elements, for example sodium chloride. What will happen if we put these two most reactive elements like metal, sodium from group 1 and non-metal, chlorine gas from group 17 together? Let's see how they make bond together, or how they react to each other when a small piece of sodium is added to the yellow-greenish chlorine gas. They are going to form an ionic bond, which gives us simple salt sodium chloride or table salt. Their reaction produces a great deal of heat energy, bright yellow light, fumes of sodium chloride, and of course white crystals of sodium chloride. For better understanding of their reaction, we need to know their atomic structure. Atoms tend to be reactive when their valence shell or outermost shell is incomplete. To achieve a complete stable or a closed shell, an atom does one of the three things: lose, gain, or share its valence electrons with other atoms. Valence electrons are the electrons present in the outermost shell of an atom. Valence electrons are responsible for the reactivity of an element. They determine how willing the elements are to bond with each other to form new compounds. If the valence shell is full, then the element does not want to gain or lose an electron. In this diagram, for better understanding, the pillars represent electrons and the roofs represent subshells and energy shells. If we see the electron configuration of sodium atoms, we can find that the first energy shell is full. Its 1s subshell is full with 2 electrons. Then the second energy subshell, sodium, first fills out its 2s subshell with 2 electrons, and then 2p with 6 electrons, and after that it is only 1 electron left, and that goes to the 3s subshell. That is its valence shell or outermost shell. Sodium will be more than happy to give away that 1 valence electron. It really gives sodium a pain because every atom wants to have a full valence shell. If sodium gives away 1 electron from its valence shell, then its valence shell will be 2p6, and this is fully loaded with 6 electrons, and the second energy level of sodium will be full. If we look at chlorine electron configuration, we can see that chlorine first energy shell is full. Its 1s subshell is full with 2 electrons. Then the second energy shell is full. Its 2s subshell is full with 2 electrons, and the 2p subshell is full with 6 electrons. And in the third energy shell, chlorine first fills out 3s subshell with 2 electrons, and 5 electrons goes to 3p subshell, which is 1 electron short of having the full outer shell or valence shell. It is so close, and chlorine is unhappy because its valence shell is not full. So sodium and chlorine both are unhappy with their valence shell, and both want to fix their valence shell. In trying to fix it, that is how they end up with forming an ionic bond. To fix the situation, sodium will give chlorine its 1 valence electron. Chlorine is super hungry to get 1 electron from sodium. Now the chlorine 3p subshell is filled with 6 electrons and makes chlorine is more stable. By giving away 1 valence electron to chlorine, now sodium has become more stable because its second energy shell has become its valence shell, which has the maximum number of electrons. We know that the two oppositely charged atoms stick together, attract together, or glue together to form a new molecule or compound. Here, positively charged sodium ions and negatively charged chloride ions stick together to form sodium chloride, known as table salt. When ionic bonding starts, sodium and chlorine atoms do not have a charge. They had the same number of electrons and protons, and they were neutral. But when they give away electrons, or take electrons, then their electrons and protons number become different, and they get charged. For example, chlorine atom had 17 electrons and 17 protons before bonding, but after taking one electron from sodium, its total electrons has become 18. That means more negative charge electrons than positive charge protons, and it becomes an anion, negatively charged chloride ion. Sodium also had 11 electrons and 11 protons before bonding, but after giving away one electron to chlorine, now its total electron number has become 10 electrons and 11 protons. That means more positive charge protons than negative charge electrons, and sodium has become cation. Thank you for watching. Don't forget to subscribe, like, and share this video.